right, so now that we've been factoring for a couple of days, what we're going to be doing today is using what we know about factoring with sum and difference of two cubes, quadratic patterns, and just kind of review of factoring from previous classes before Algebra 2. We're going to be using that to solve. So the first thing that we're going to talk about in terms of solving is the fundamental theorem of algebra. And what the fundamental theorem says is that an nth degree polynomial function has exactly n zeros. And remember that zeros means the same thing as solutions or roots. So meaning what we're going to be doing is we're going to be looking at the highest degree of the polynomial, and that highest degree is going to tell us exactly how many solutions or zeros or roots our polynomial equation should have. So for example, if we look at the equation 4x to the fourth minus x to the third minus 3x squared plus 9x minus 10 is equal to 0, I'm going to look at the highest exponent here, and that's going to tell me that if I were to take this equation and solve it, I should have 4 solutions. Which if we look at the next example, how many zeros does the function 24x to the 8th plus 5x squared plus 4x plus 20 have? Again, we're looking at the highest exponent. So if we want to say how many zeros this function is going to have or this equation should have, it's going to have 8 zeros. And remember that zeros in terms of graphs is where the graph is crossing the x-axis. So that means that this graph should potentially cross the x-axis 8 times. So now that we know that, let's go ahead and find some solutions. So we want to find the solutions of this polynomial 8x cubed minus 27 is equal to 0. So if I look at this highest degree here, I should know right off the bat that I should have 3 solutions at the end. So I'm looking at these numbers and I'm recognizing I definitely have an x cubed, which means that this would probably end up being some sort of sum or difference of 2 cubes. And 8 is a perfect cube, 27 is a perfect cube. I've got a minus in between here, so I'm going to use my SOAP factoring pattern. So I'm going to go ahead and set up my binomial. I'll set up my trinomial. And this time I am solving an equation, so I want to make sure that I'm bringing down the equals to 0. So my binomial is going to be the cubed root of 8x cubed, which is going to be 2x. Cubed root of 27, which is going to be a 3. Same sign, so minus. And then my trinomial, my first term is going to be 2x squared, which is going to be a 4x squared. My middle term is going to be 2x times 3, so a 6x. My last term is going to be 3 squared, which is going to be a 9. So then I'm going to have the opposite sign here, so plus, and then always positive. So the difference between what we were doing the last couple days and now is once we had done our SOAP factoring the last couple days, we were done. But now we want to know, what are the solutions? What are the zeros? So I'm going to use my zero product property at this point because I know that I'm not going to be able to factor this any further because if we check the discriminant, it's going to be negative. I'm going to use my zero product property to separate out my factors and set them both equal to 0 in order to solve for x. So then I can go ahead and take this 2x minus 3 is equal to 0. That's going to give me a 2x equal to 3. That's going to give me an x is equal to 3 halves. So that's one of my 3 solutions. But this one over here, we said that it's definitely not going to be factorable. So my only other option to solve a quadratic trinomial that's not factorable is to use the quadratic formula. So I'm going to set up my quadratic formula, opposite of b, so -6 plus or minus the square root. I'm going to go ahead and calculate my discriminant. Looks like it's going to be -108 divided by 2 times my a value of 4. And then I'm going to go ahead and keep on simplifying. So I always want to make sure that whatever's underneath the root is in simplest radical form. So if I'm looking for, I believe this is going to be, well, I can separate it into its real part and its imaginary part first. And then I'm going to simplify the radical. I think the largest perfect square that goes into 108 is 36. So So I think that breaks down into 6i root 3. And then I'm noticing that everything is divisible by 2 here, so I'm going to break it down. I'm going to say that my two solutions for this quadratic trinomial is going to be -3 plus or minus 3i root 3 all divided by 4. And this is giving us two solutions here because one of them is going to be -3 plus 3i root 3 divided by 4. The second one is going to be -3 minus 3i root 3 divided by 4. So here's two of our solutions right here. And then our other solution over here was x is equal to 3/2. So there's where my three solutions are for this one. So even though we did end up getting something that was not factorable, we can still use the quadratic formula. Even if our solutions are going to be imaginary, we want to make sure that we're getting all of them. So let's look at another example. So 3x to the 5th minus 15x cubed is equal to -12x. Similar to what we were saying when we were solving quadratic equations is we always need to make sure one side of the equation is equal to 0 in order to solve here. So if you notice that you've got terms on one side of the equation that can get moved, move them first. So you always want to get one side equal to 0 before we can go ahead and actually factor. So I'll move the 12x to the left-hand side. And then I'm noticing I have definitely a GCF to take out here. I've got a 3 and an x that I can take out. So that will leave me with an x to the 4th minus 5x squared plus 4. And in every single step, you should be bringing down the equals to 0. Do not drop that because you want to make sure that you're bringing down an equation in every single step that you are doing. So then once I take the GCF out, I'm noticing that I have a quadratic pattern in here because I have a highest degree of x to the 4th, and then my next highest degree is half of that. So I can factor this as if this was a regular like x squared minus 5x plus 4. And if you need to do that off to the side, you definitely can. So we're looking for factors of 4 that are going to add to -5. That's going to give me a -4 and a -1. But instead of just putting an x here and here, remember that we want to use an x squared. And again, I'm bringing down the equals to 0 here in this step as well. So then I'm just looking to see, okay, well, can I break these down any further? I can, because both of these are differences of two squares. So I'm going to use my differences of two squares factoring pattern to write this as x minus 2 and x plus 2. Write this as x minus 1 and x plus 1, all equal to 0. And notice that also in every step, I'm bringing down the GCF of 3x, so don't drop that either. And at this point, everything's broken down into its smallest factor. So this is where I can go ahead and use my zero product property. And if you notice up here, we should have 5 solutions because our highest degree is 5. So I'm going to set my first factor of 3x equal to 0, set x minus 2 equal to 0, x plus 2 equal to 0, x minus 1 equal to 0, and x plus 1 equal to 0. So I'm just pretty much separating out each one of these factors using the zero product property to get me an x value of 0, an x value of 2, an x value of -2, x value of +1, and x value of -1. So here are my 5 solutions. And in this case, these are all real solutions. So sometimes you might just get all real solutions. Sometimes you might get a mix between a real solution and an imaginary solution. Sometimes you might just get imaginary solutions. It really just depends on the equation that you're solving. All right, let's look at a couple more. So example 4 is a 4-term polynomial. Everything's over to one side. I've got one side equal to 0. So anytime you have a 4-term polynomial, hopefully you're thinking to yourself that you might be able to use a factoring by grouping method here. So I'll group my first 2 terms together, group my last 2 terms together, take out my GCF here of x squared. That would leave me with an x plus 3. My GCF of 4x and 12 should be a 4. That will leave me with an x plus 3. And again, I'm going to bring down the equals to 0. And then it looks like that's going to give me a factor of x plus 3, and that's going to give me a factor of x squared plus 4. Again, bringing down the equals to 0. I can't break down either one of these factors any further. This is not a difference of two squares. It is a sum of two squares, and we do not have a factoring pattern for that. So at this point, I'm going to go ahead and I'm going to separate these out to use my zero product property. And if I'm looking at the highest degree of my polynomial, I know that I should be looking for three solutions here. So this x plus 3 is equal to 0 is going to give me one solution if x is equal to -3. And then this x squared plus 4, I can use square roots to solve this. So if I bring the 4 over to the other side, I'm going to get an x squared is equal to -4. And when you take the square root, remember that you're going to get a plus or a minus here. So this is where your other two solutions are going to come from. If you just take the positive root, you're automatically eliminating one of your solutions. So make sure that anytime you're taking a square root, it's going to be a plus or minus. And then this is going to be an imaginary solution, but we do know how to work with that. So I'm going to turn that into x is equal to plus or minus. I can write that as I times the square root of 4, which is going to give me x is equal to plus or minus 2i. And those are our other two solutions. They're imaginary, but two solutions here, one solution here. Highest degree is 3. That gives us our three solutions. All right, we'll look at example 5. This is another quadratic pattern that we talked about on the kind of first day that we were talking about quadratic patterns. This isn't an obvious one. A lot of people kind of miss the fact that this x to the 4th is actually a perfect square. But remember that anytime you do have an even power exponent, that does indicate that you do have a perfect square. So this is a difference of two squares because x to the 4th is a perfect square. 144 is a perfect square. There's a minus in between them. So I'm going to go ahead and I'm going to use the difference of two squares factoring pattern. So when I'm trying to decide what my first two terms are going to be, I'm really taking the square root of x to the 4th, which really means I'm looking for two terms that are multiplied together that are exactly the same. That's going to give me an x to the 4th. And if I think about what that would be, that would have to be an x squared times an x squared. Same thing being multiplied together, x squared times x squared just give us x to the 4th. So an x squared here, an x squared here. Take the square root of 144, which is going to be 12. And then one's going to be plus, one's going to be minus. And then I would just want to check to see if I can do anything else with these factors. So x squared plus 12, I don't have any GCF or anything to take out of here. X squared minus 12. This is a perfect square, but since 12 is not a perfect square, this is not a difference of two squares, so I can't break this one down any further. So at this point, I'm going to go ahead and use my zero product property and say that I'm going to get an x squared plus 12 equal to 0 and an x squared minus 12 equal to 0. And again, if we're checking our highest power here, our highest power is 4. So this should give us 4 solutions or 4 zeros at the end. So I'll work with the x squared plus 12. So I'll move the 12 to the other side. It's going to give me x squared is equal to -12. Going to go ahead and take the square root. And again, as soon as I'm taking the square root, I'm going to go ahead and put my plus or minus in, which is indicating that I have two solutions here. And then I'm going to put this in simple radical form. So x is equal to plus or minus I root 12. And if I take that and do my simple radical form, I believe that will give me 2i root 3. So my first two solutions are imaginary. Then I want to work with my second two solutions over here. So I'll move the 12 to the other side. That's going to mean x squared is equal to 12. Take my square root. Again, as soon as I'm taking the square root, plus or minus, here's my other two solutions. And then this is a real root, so I don't need to worry about any i's here. So just put that in simple radical form. So my other two solutions are x is equal to plus or minus 2 root 3. And again, two solutions here, two solutions here. That's going to give us the 4 solutions using our fundamental theorem of algebra. All right, so the last problem that we want to look at is example 6. So we have an 8x to the 7th minus x to the 4th minus 8x cubed plus 1 is equal to 0. So this is a 4-term polynomial here, so chances are we probably want to group. So I'll go ahead and do my grouping here. Take out my GCF here of my first two, which is going to be an x to the 4th. Looks like that's going to leave us with an 8x cubed minus 1. Over here, I'm going to take out a negative 1 as my GCF, which leaves us with an 8x cubed minus 1. And again, I want to make sure that I'm bringing down the equals to 0 in this step. So then it looks like our factors are going to be an 8x cubed minus 1 and an x to the 4th minus 1. And actually, I can do something with both of these. So this first quantity is actually a difference of 2 cubes because everything here is perfect cube. We've got a minus in between, so I'm going to use my SOAP factoring pattern here on this one. So set up my binomial, set up my trinomial. So square root or cubed root of 8x cubed is 2x. Cubed root of 1 is 1. Same sign. Take this 2x and square it. So that's going to give us a 4x squared. 2x times 1 is 2x. 1 squared is 1. Here we have an opposite sign. Here we have an always positive. And then I want to take care of the x to the 4th minus 1. This is actually a difference of 2 squares similar to what we had in example 5. X to the 4th is a perfect square. 1 is a perfect square. There's a minus in between here. So I'm going to go ahead and I'm going to break that down using my difference of 2 squares factoring pattern. So again, to get an x to the 4th, I'm looking for 2 values that multiply together that are exactly the same that are going to give me an x to the 4th. So that's again going to be an x squared and an x squared. Square root of 1 is 1. And then one of these is going to be plus, one of them is going to be minus. And then again, in this, I'm making sure I'm bringing down the equals to 0. And then I'm just going to look over these and say, okay, is there anything else I can do with any of these? The 2x minus 1 I can't do anything with, so I'm going to go ahead and bring that down. We know that this discriminant is going to be negative, so I can't factor that any further. X squared plus 1, that's a sum of 2 squares. We can't do anything with that. But then this x squared minus 1 is a difference of 2 squares, so I can go ahead and use the difference of 2 squares factoring pattern on this one. So x minus 1 and x plus 1. And again, bring down the equals to 0 in every single step. So at this point, this is where I'm going to go ahead and separate all of these out and use the zero product property to solve. So 2x minus 1 is equal to 0. 4x squared plus 2x plus 1 is equal to 0. X squared plus 1 is equal to 0. X minus 1 is equal to 0. And x plus 1 is equal to 0. And here we know that we should have 7 zeros altogether. So at the end, we should have 7 zeros or 7 solutions. So if I solve out this 2x minus 1 is equal to 0, that's going to give me an x value of positive 1/2. Here, we know that this is not going to be factorable. So again, we do want to use the quadratic formula to help us solve this one. So set it up. X is equal to opposite of b, plus or minus. We'll go ahead and calculate my discriminant here. Looks like that's going to be a negative 12. All over 2 times a, so 2 times 4. I'm just going to simplify this. I'm going to definitely break down that square root, put that in simplest radical form, which actually we did up here in example 5. So I know that the square root of negative 12 is equivalent to 2i root 3. And then divide it by 8. And then I can definitely divide everything by 2 here. So x is going to be equal to negative 1 plus or minus 1i root 3, and then divided by 4. So that gives us 2 imaginary solutions. So we have 1 real solution. We have 2 imaginary solutions. Next, I'm going to work with this x squared plus 1 is equal to 0. Here I can use solving by square roots. So I'm going to move the 1 to the other side. That's going to give me an x squared is equal to negative 1. Take the square root. Again, as soon as I do that, I'm going to make sure to put my plus or minus in. And then we know that the square root of negative 1 is equivalent to I. So my two solutions here are x is equal to plus or minus I. And then here and here, these are going to be easy zeros. So this one's going to be an x value of +1, and then this one's going to be an x value of -1. So we can just make sure that we have all of our solutions. We have one real, we've got two imaginary, so that's 3 altogether. We've got two more imaginary, so that's going to be 5 altogether, and then 6 and 7. All right, so now it is going to be your turn to practice. Please let me know if you have any questions.